Thank you. Let's see if this works. Yes. So I will talk a little bit about a project that I worked on a while ago, which is generally about dynamic verification, specifically testing of stateful OCaml programs. Just a few words about me. I'm originally from Austria, where I did my undergraduate degree at the University of Technology in Vienna. Then I moved to the very far north of Sweden, where I did a degree in space engineering, so something completely different. And then I thought, well, this isn't theoretical enough, so I'm going to do a PhD in computer science at the University of Uppsala. And for those of you who do a PhD or have done a PhD, you know how it goes. It takes forever, and at a certain point you think maybe I should do something else. So I did an internship at a company called Talides, which I guess the majority of you actually know about, which was very fun. I was for 3 months in Paris, right at the time when the Summer Olympics happened, which was in retrospect not the perfect time to be in Paris. But it was quite fun because it seemed like every week they were looking for another French politician that had to jump into the Seine to figure out if it was safe to swim in it. Which, if you think about it, is actually also a form of testing. So that was quite fun. And then eventually I actually did finish my PhD, and I'm now a research associate at the university, where I also work mostly on verification, but more on static verification, not dynamic verification. So the majority of this talk comes from work that I did at Talides, and we ended up writing a paper about this. So if you want to know a bit more about this, then I would invite you to look at that paper. I presented that at TACAS last year. And very surprisingly, we actually ended up winning the best tool paper for this. Just about testing. We did this in 2025, not in 2024. So there's an off by 1 year in this. But yeah. So I don't have to tell you what OCaml is and why it's cool to use OCaml, right? But just to kind of prepare the stage a little bit. So OCaml is a mostly functional programming. But first and foremost, it's a functional programming language. But it does try to not get in the way of actual software development too much. So there's many like imperative features that make programming in OCaml a lot easier. So we have things like references, we have things like mutable arrays, we have things like input-output, and we have exceptions that are just part of the language, right? And from a verification point of view, those features make verifying OCaml programs interesting, or depending on who you ask, difficult. And I also don't have to tell you that there's many tools that are implemented in OCaml that are actually industrially used, right? So we have especially a lot of verification tools that are implemented in OCaml. And so one would almost assume that if we spend so much time doing OCaml to verify other programming languages, we would have like the same kind of attention on OCaml itself as well when it comes to verification, and that is not necessarily the case. So it has gotten a little bit better over the last years, which I think can kind of at least in part be traced back to the inclusion or the creation of a specification language for OCaml. So there's this Gospel project, which extends OCaml with a behavioral specification language. So if you know languages like ACSL for C or JML for Java, this is basically the version for OCaml. And so what Gospel allows you to do is that you can express things like type invariants, function, pre-post conditions. You can talk about mutability. You can talk about exceptions and a lot of other things within the Gospel kind of framework. And Gospel itself is completely tool agnostic. So similarly to ACSL and C, for example, these are just comments that you put in your code. The compiler is completely oblivious to what the Gospel annotations are, but you can then provide tools that actually work with these annotations. And by now, there's a couple of them. The one that I'm going to talk about today is ORTAC, because that's the one that I worked on while I was working at Talides. And what ORTAC kind of is based on is this framework of property-based testing. So property-based testing is a particular form of testing that was popularized by the Haskell library QCheck. And there is by now an implementation of QuickCheck for almost any kind of programming language. And the one that exists for OCaml is called QCheck. And without going too much into the theory of property-based testing, you can think of a property as just a function that returns a Boolean, right? So the property is always something that you can evaluate to be true or false. And as an example, you can, for example, say that list revolution is idempotent. So if you reverse a list twice, what you get back is the original list, right? So that's a function or a property that takes in a list of any kind of type and it returns a Boolean. So that's a property. And what you can then do is you can define a test. This is the property. You can define a test, and the kind of nice thing here is that you define a generator. So you say, well, test this property on different lists of here, for example, small natural numbers. There's other combinators here, so you can have small integers. You can just have just integer, and these are fairly smart. So they are done in a way that, for example, they test edge cases. So they know, okay, if I'm doing this on integer, then it will try like the biggest integer, the smallest integer, 0, -1, all the like normal cases where things could go wrong. It tries to test these. And then you can define there's different ways of how to actually run these tests. This is the simplest one where you just run it and where you expect that it could throw an exception. What's quite nice about this is not like a lot more code than you would write for a normal unit test, right? So there's not really a lot for you to write, and this works very well on functional or immutable data types, right? If I have a property on an immutable data type, then I can very easily write these kind of properties. This does not really work if I have state at all. So if I was working on a stateful data type, like a stack or a queue, then these properties I must formulate that differently, because I can't just have these kind of these functional properties. So this is where QCheck-STM comes in. So QCheck-STM is basically an extension of QCheck with state. And it allows you to do something that's called closed box model-based state machine testing. So what that means is that you're basically comparing two different systems. So you have something that's your system under test. So that's an instance of the data type that you're trying to check. So for example, a stack. And then you have an immutable model of that. So for a stack, that could, for example, just be a list. And what you then do is that you run sequences of API calls on your system under test. And you also run equivalent operations on your immutable model. And then you compare them with each other. So for creating, there's usually not much to compare. If I push a value onto a stack, there's also not really much that I can compare, because it's a closed box, so I don't really see what's happening on the inside of these data types, right? But when I pop a value, then I can compare if what I get back from my stack and what I get back from my immutable model, if that's the same value. And if not, then I can report this to the user. So what does this look like in code? And this is heavily simplified. So what you would have to write is a lot more, but just to give you kind of a feeling of what you would need to write if you were to use QCheck-STM by yourself. You have to define a type system under test. So this, for example, here is an integer stack. And you have to define a type state. That's the immutable model. So here I say, okay, this is the integer list. You have to give a function in its up that knows how to create an element of that system under test, and equivalently, you have to give the initial immutable model as well. Then you have to define the type command. So this is where you give the kind of description of the API calls that you can do, right? So for a stack, for example, I can push. Here I can push an integer. I can pop, and there's many other operations. So this is all kind of a setup that QCheck-STM is set up as a functor. So this is kind of like a model that you have to provide, a module that you have to provide to a functor that then creates the testing code for you. You have to provide a function that creates arbitrary commands. So this generator module of QCheck actually has combinators like one of that, like a list of different elements. And then Here, for example, if I have a push, well, I also have to create a random integer that I'm pushing, right? So this is actually the random integer generator. Then I say, well, map this and wrap this with a push, with the push constructor. I have to define how a command works on my immutable model. So if I push, for example, I just put this on top of the list. If I pop, well, then whatever is left is just the tail of that list, right? Here we already see that this doesn't always work like this, because what happens if there's an exception here, right? So this is why I don't show you the pop example, because it's a bit more involved. You have to define how to actually run a command under your for your system under test. So if you have a push, well, you do stack push. If you have a pop, you do stack pop. This will obviously not type check as it is here, because this returns this unit. This returns an integer here, right? So there's actually, you have to wrap this in a kind of result monad that also keeps track of the types that are supposed to be returned. But I left that away to make it a bit easier to comprehend. And then you can have a post condition. So in the post condition, for example, as I said with a pop, if I have a pop operation and I get a return value R, well, then I can look if R is actually the same as the head of my list currently. So this is something where I then could check that this, if this R holds good. So you can write this by hand, and it's not particularly difficult because it's fairly kind of mechanic. But there's a lot of code to write, especially if you have lots and lots of different API calls that you could use on your immutable data types. And this is where ORTAC comes in. Now, I'm fairly certain that ORTAC stands for the OCaml runtime assertion checker. The thing is, while I worked with this, I never asked what this actually stands for. But this is the only thing that I could come up with, and this makes a little bit of sense. So I hope that that's the name. Otherwise, maybe somebody just thought that ORTAC is a cool name. But I'm fairly certain that's where this name comes from. The idea of ORTAC is that you take your module interfaces for your stateful data types and you annotate them with gospel contracts. Specifically, you annotate the particular data type itself, which by convention is usually called T, right? And then you specify gospel contracts for the different API functions. And what ORTAC then does is that it creates code for testing for you. And ORTAC, again, is a kind of like very open architecture, so you can have different plugins that then take this code for testing and do different things with it. There's a couple of them by now. The one that I'm going to talk about is QCheck-STM plugin, because that's the one that allows you to have these this kind of like quick check-like testing for these kind of mutable data types. So again, if we look at the stack, and we have a couple of API calls that we can do on the stack, what does this look like with gospel contracts? Well, first of all, I have to annotate my data type. So here I have a mutable model contents. I could give that another name as well. And I say I model this as a sequence of values. This is kind of gospel lingo. So right now there's still sequence and lists. I'm not entirely sure what the difference between them are. So lists are also going to like disappear in a future version of gospel. So for all intents and purposes now, think of sequences as lists. If I create a value of a stack, then I ensure that like the contents field of my model is empty. If I push a value, well, then I just cons the value onto the old. So if you've ever worked with ACSL or JML, then you are aware of this old operator that basically allows you to refer to the model before you do the function call. And this is the one after the function call. And you also have to specify which fields you're actually modifying. So you could have different model fields, and not all of them need to be mutable. So it could, for example, be that if you're specifying an array, you could have a second model field size that's actually not mutable. That always must be the same. You could equivalently also write that down as an invariant, but that's usually just more cumbersome. And then we have a function like isEmpty, where we just look at the length of the list and then say, okay, if it's 0, then the return value is true, otherwise it's false. So this is intentionally done in a way that this looks very much like OCaml code, right? So this is not particularly hard for an OCaml programmer to learn, which, as somebody who has also worked quite a bit with ACSL, I have to say this is a lot nicer to work with than ACSL. And you also need to provide a configuration module. So this just, because usually these data types that we work with, they are polymorphic, right? So you have to fully instantiate it. This is something that when I worked at Tidus, we actually thought about getting rid of this by kind of just randomly instantiating these. I don't think that this has happened yet. But basically, if that happened, then we could get rid of this configuration module altogether. But there's a couple of other things that you can do in the configuration module as well. So you can you can tweak the generators for values in here. So if I, for example, have an API call that has an integer parameter, and I wanted it to only use positive numbers, then I could, in here in this configuration module, tweak the integer generator to only create positive values, for example. How do you actually run this? So you run ORTAC with the QCheck-STM plugin. You give it the module interface that's annotated with your gospel contracts. Then you give it the configuration module, and it will generate code automatically that does this runtime assertion checking. So it does this kind of property-based testing. So the property that's tested here is kind of that random sequences of API calls align both on your system under test and the immutable model that you have, right? That's kind of the property that we're testing. It needs a few additional libraries to link. So there is a Dune plugin available that I'm not going to really talk about here. And it can quite easily be integrated into this integration as well. And if you want to know more about this, the easiest way is to look at the ORTAC Git repository, because there it's actually set up so that it's automatically, whenever we change to the tool, it's running it on a couple of tests to see if it's still working. Now, we'll have a little bit of time. So something that I specifically worked on while I was at Tidus was, all I showed you right now were API calls that worked on one system under test, right? But if you look into the APIs that are available for things like stacks and queues, even in the standard library, there's a couple of functions that actually take multiple sub arguments. So, for example, here you have a copy function, right, where you can take a stack and you can create a new instance of that stack that's independent of the first one. The contract for this is very easy, and you could also already specify this when I started my internship. ORTAC just ignores things that it doesn't understand how to work with. So here, for example, it would see, okay, well, it's taking it's using two different SATs. So it takes one and then returns one, so it doesn't know how to work with that, so it would just ignore this function. At the end of my internship, actually, this worked as well. And you could also test things like transfer functions, where you have two sub arguments and you transfer, in a stack case, for example, all the elements of the first stack onto the second stack. The way that this works in the back is that you're actually using a stack. So you have not just one system under test, you have a stack of system under tests, and the immutable model is then a list of immutable models. So it's taken care of in the back, so you don't have to think about this. But this allows us to also now test functions that actually create new sub-elements, which we couldn't before. And it allows us to test functions that have multiples. Now, what could we actually find with this? So the coolest bug that we could find was in the standard library, which I didn't think that I would find something there. So when I actually found something, I went to my supervisor and was like, our tool is broken. Why? I was like, because it failed on something from the standard library. And then he came back an hour later and was like, no, there's just an error in the standard library. Yep. I did not believe that that's an option. When I specified the hash table library, what I did was that I looked at the create function, and it says here, right, hash table create. It's a new empty hash table with initial size n. For best results, n should be on the order of the expected number of elements. We all know how hash table works. So what I thought, well, as a model, I'm just going to use an association list, right? So I'm just going to use a list that kind of associates keys with their values. And then the create function, if you forget about the Boolean random value, checks that the size is bigger or equal to 0, and then ensures that the contents field or the contents model field is empty. So it's just an empty list. Checks is a particular form of what's called a precondition. So you also have something called requires. With a requires, the thing is that the assumption is you cannot call a function if the requires clause is invalid, right? So like it has to be valid for this function to be available to you. Checks is a shortcut of saying, well, you can still run this, but you're going to get back as an invalid argument exception. So you don't have to kind of like, because it makes the contracts a bit easier to write. So I thought this is a fairly kind of like, a fairly standard way of specifying a hash table. So when I ran this, what I got back was this, which what's quite nice about this is that it actually gives you examples, right? So it gives you an example program showing you, okay, this is where you see a failure. So it creates one sub-argument, and then it tries to create another one, but it's using a negative initial size case. And so what we said, because we had this checks clause that says size must be equal to 0, says, well, I was expecting an error, but what I got back was okay. So what it turns out is that in OCaml, in the standard library, you can actually give to the hash table create function negative initial size case. It's perfectly valid. Which there was then a discussion on the compiler team if that should be changed. What they ended up doing is that they changed the documentation of the create function. So now it mentions that you're allowed to give it negative initial size case, but you probably shouldn't. But it's okay. So like if you give it a negative size case, what it's doing is just using 0, which is an option or it's a design choice. But I was not imagining that we would find anything in the standard library that was actually worth bringing up at all. So that was pretty cool. We did find a couple of other things as well. We had this documentation fix in the hash table create function. Then we had 2 bugs in a library for variable sized arrays, out of which I think one of them is still not fixed. So we found the bug, but I think we're still not entirely sure why it's happening. We found 7 bugs in a bit vector manipulation library. Out of there's a couple of like different ones that we found. So we found a couple of integer overflows. We found a couple of division by zeros, and we also found functions that were throwing exceptions that we weren't expecting to be thrown. And all of them have been fixed by now. And the hope is obviously that eventually, if we get more and more modules actually specified with gospel, that we will find more and more errors eventually. And I'm pretty sure that since I was at Talides, they have found others that I'm not aware of with this tool. But I think, if I'm not mistaken, the gospel website actually had a list of errors that were found. So there's a kind of like, if you want to, right now it's a very easy way to get onto that list. It's just to go onto the OCaml repository, look for something that looks like a mutable data type, write a specification for its interface, and you will most likely find something. Like this is the chances of you finding something in code that's out there are very high. So that's actually all for me. Thank you. And if there's questions, then. Yes. Should I, like, you said something about a microphone thing, but it says audience microphone and it's green, so.
Maybe I forgot to disable it. Okay. I have one kind of meta question. I spend a lot of time in the Rust community, and we've been trying to come up with a common assertion language, like specification language for ages, and nobody can agree.
Yeah.
And would you say that Gospel for this was just the good language that you needed to have, or was it just there and then you used it and wouldn't change it if you could, if you had like?
I think Gospel was something that solved a need, and it was a very, there's bits and pieces in the Gospel language that are very kind of ad hoc resolved, where you saw either somebody just chose, was like, okay, we're gonna do it this way, or there was potentially a little bit of conversation, and then somebody said, no, we're gonna do it that way. So there's a couple of things that could be done better. Like, as I said, for example, I never fully understood the difference between sequences and lists. And then there's a thing where like the list, the Gospel list module has like certain API calls are different to like the list module of the OCaml language. Like when you do a map, like the function comes after, or at least kind of like this. So like the order of arguments isn't exactly the same between OCaml and Gospel. So there's a couple of these where it started as an academic project. It is still mostly an academic project. I mean, I guess there's quite a lot of research also going into the design of these kind of specification languages. None of them are super nice to work with, I have to say. I haven't encountered one yet where I was like, okay, this is amazing. I would love to work with this. They all just are like different kinds of painful. And Gospel so far is the one that I experienced that was the least painful. But it's still painful. So it's like,
like being expressivity. So, for instance, your copy spec says that the content of the target is the same as the content of the original value, but it doesn't say that if you mutate the target, it's the same. It doesn't modify the original value.
Yes, so
And
it
that's a
assumes
mistake.
yes, it is. So there's a couple of things. So Gospel is going to change. I know that there's like a new version of Gospel coming out, and it's going to change quite a bit. So I'm not entirely. But what I'm selling right now is what Gospel was like when I worked with it 2 years ago. So there was a couple of things that you could just write out and not specify. So there was a discussion. If you work with ACSL, for example, ACSL allows you to express something that looks very similar to separation logic, because obviously when you have pointers in C, you have to be able to say, well, could these two things be aligned, or do we always point to different things? In Gospel, they just assumed that like if you give two sub-arguments, they're never the same. I don't know if this is planned, that this is a feature that you could say, well, if I give you two stacks, could they actually be the same stack? I don't even actually know how the transfer function works on stacks if you give it twice the same stack. I mean, that's probably a way to come up with how this works. So what also doesn't really work that well right now in Gospel is specifying higher order functions, because it's a bit of a like, how do you do the functional contract of something that returns a function? Like, what's the contract of the function that's returned? And so for when I worked on ORTAC, for example, higher order function, which is not tested at all, which is of course a serious limitation for a functional programming language. By now, they are actually tested as long as you only have second order functions, and as long as I think the function that you're giving as an argument doesn't have more than 4 arguments itself. There's a couple of weird kind of and then there's like when you like do tuples, for example, you have a tuple argument. Your tuple is not allowed to have more than I think arity 10, because afterwards QCheck doesn't know how to create random instances of it anymore. So it's like, then how often have you seen an API call that has a tuple with more than 10 elements, right? So like, some of these are also like practicality things, but there's definitely room for improvement. And I think one of the biggest problems of Gospel right now is also just the missing user base. So there's not really that many people in the discussion about how the language should evolve. So if more people were to use it, I think it will also kind of evolve more. But I do understand it's coming up with these languages is extremely difficult. So I'm not surprised that in Rust it's not a
So I suppose one of the benefits of property-based testing is that it's typically pretty simple. Like you could write down a list reverse property in terms of reverse, right? You would typically write down properties in terms of your own system. And I suppose I can imagine one of the difficulties here is that you now have to write down your specification in terms of something else, right? You have to write down your specification for a stack in terms of a list. And for complicated systems, that might not be feasible in some cases, or it might be difficult. Can you do a similar thing here to what you could do with property-based testing and say, for example, with our stack, we should expect that if we push and pop n times and we push and pop n+1 times, like we should get some expected relation between the two or something like that?
Yes, I'm fairly certain that you can. I think the idea with QCheck-STM particularly was to be able to eventually be able to really test all the API calls that are available for a particular data type, right? So for particular things like, saying, well, push and pop have a certain relation to each other, that I can actually write down as a property, right? So I can probably write this down as a kind of, I don't know, linear logic formula probably to be like, okay, if you push 3 times, you pop 3 times, this is what you're expecting out of this. Both are valid. Like I don't see why one of them would not be a good way of testing either. I think the one of the kind of big problems with these specification languages is also that they are just like extremely verbose. So I know that there was a project a while ago where they were trying to fully specify and verify like the bigger part of a C standard library or a C++ standard library. And if you look into the specification code, there's like per file, there's like, like 10 lines of C code and like hundreds of lines of specification code, which, it's like, if you get to the point where there's like a very select few people on earth that can actually read your specifications, it's like, well, what have you won in the end? So it's, and this is also something, if you look even at these contracts, right? I mean, they're already getting quite big for what they're doing.
So I guess that's what I was getting at. Like for property-based testing, you only need kind of a partial oracle. You only need to be able to say some property holds for our system. Whereas in this case, it seems like you need to be able to solve the oracle problem and say we have some complete specification that holds.
I mean, there's a couple of things here. There's also something that I haven't talked about, like ORTAC. Gospel allows you to specify things that are not executable. So all the code that you've seen here, right? These were all kind of a subset of Gospel that can be turned into executable code. But obviously, there are certain properties that you can write down that aren't executable, at least not in the way that they're written down. And so it kind of only really accepts a subset of Gospel altogether. The thing is also, nobody forces you to specify everything, right? It could be that you are only interested in a particular sub-behavior of your particular data type. So this is something where you can get a bit of a handle of like how big your contracts become. It's like these contracts, they don't have to be complete in the sense that they encapsulate the full behavior of what your data type is able to do. But then obviously you can also only test the parts that you're specifying.
Partially answered my question, but I was going to ask, is there kind of a verification of the specification that you write? So, I mean, I guess, is it garbage in, garbage out kind of situation? So if you write like an inconsistent
checker.
Okay.
So it doesn't allow you to write stuff down that doesn't type check, and it also checks it against the annotations of the actual OCaml code. So you can't say, this is an integer, and then in the specification you say, oh, it's a boolean.
But in practice, when you were writing these specifications for a library, how confident were you that you were writing them correctly?
It's an extremely good question. When I was teaching, I'm not teaching that course anymore. When I was teaching formal verification and we did contracts in SSL, I always told the students to try and make the contract as different to the actual source code as you have. Because I mean, if you're basically just copying what's in the source code, right? Like even very simple examples where you have a max function and they just copy like the if statements into the contract, which you can do in ACSL, but like obviously they align with each other. But if you can find like a formalization that actually uses like a mathematical way of expressing this, right? Then I would say that's the one to go for. And also in the best case, you actually have two different people. You have one specifying and one implementing. And so your chances that like both of them do exactly the same thing and like actually have the same kind of era of thinking about stuff while they are writing it down is just smaller. But yes, I mean, in the end, it's one of these things that when you read a paper where it says like, oh, we have verified this. It's like, no, you've checked it against the specification, but nobody told you that the specification itself is correct, right? So you have to always take it with a bit of like a grain of salt, being like, okay, you could show that your implementation is according to a specification, but how correct your specification is a like completely different question.
Thank you.